Yeah. So, welcome to the seventh week of this problem solving season. So, in this week, the topics covered were based upon the transaction management and the concurrency control. So, let's wait for 1 or 2 minutes, let others join, then we will get started. So, in transactions, we will see about some questions about serializability, then uh, about deadlock conditions, and some theoretical questions if possible. So, okay, so I think we should get started now. So, these are previous year questions only, and with the help of questions, I will try to cover the concepts which are taught in the lectures with some examples. So, the question is about the schedules. Schedules are means a set of transactions at a time. So there are four transactions given, and considering them, uh, there is Rx for read operation, there is Wx for write operation, and we have to select the correct options among them. So the first thing we should know is yeah, Satyanarayan. Any question? There is nothing about attendance. So, so this question is all about how to declare any kind of schedule that it is serializable or not. So, as we all know that if any schedule is conflict serializable, that will also be view serializable. That is for sure. First thing. Second thing is for conflict serializability. If any of these two serializability conditions satisfy, then only we can tell that the overall schedule is serializable. Okay, what is serializability? Suppose you are given some kind of parallel executions. So if we are able to write the transactions, the operations in the given transactions in a serialized form, okay, means if it is given parallel, if we are able to solve them in sequential way, likewise, okay. So there are multiple different methods. So the best way to solve these kind of problems is to create the precedence graph. Okay, I will try to solve them with the help of precedence graph. There may be other methods, you can go theoretically, and with the help of that we will first see if there is a loop in that graph. If there is a loop, then it will not be conflict serializable. If there is no loop, that then we can say that it is actually conflict serializable. But uh, if there is loop, there is also a chance of serializability with the through the view serializable concept. Okay, so in conflict serializability, we have to look for conflicting pairs if they are occurring together. If there is any kind of loop or cycle in a operator precedence graph we will create, then we can say it is not conflict serializable. If it is not there, then we can clearly say that it is serializable. Okay, so Let's go one by one. uh, there are four options, there are four all four possibilities. So B option we can clearly neglect, because if it is conflict serializable, then it will also be view serializable. Okay, it is theoretically and conceptually wrong statement. So now we have three options. Let's see what happens. So first, I will try to check with precedence graph. We will create it. We will create a graph based upon timeline. From that graph, we will check if there is cycle or any self loop. If it is not there, if it is not there, then it is conflict serializable. If it is there, then we have to check for view serializability. If it is conflict serializable, then we can say it is a serializable. And if we want to tell about the sequence of execution of the transactions, then we will go one by one. We will check the in degrees, and with the help of in degrees we will create the flow of transaction. Okay, so let's solve it. So these are if we consider it as a timeline. So first, what will be executed? We can see rx is there in 1 second. Rx is there in T2. So first execution will be of T2. First, not going like this. First, I should write all the transactions one by one. There are four transactions. We can write it anyway. Okay, T3, T4. Okay, consider these four are four states. Okay, now we have to search for conflicting pairs. Okay, conflicting pairs means if there are some operations, those are happening on same data. Okay, so if there is read operation, there will be no conflict. Where we have to see the conflict, there is write read, there is read write, there is write write, but in different transactions. Okay, sorry, pardon. uh, so let's start it. Yeah, so whenever there is a write operation, uh, just see the example, that will be cleared. Okay, if that is not clear, I will explain it again. Okay, so just we have to see the timeline. Okay, in the timeline, if we have read operation, we have to search for any kind of write operation in other transactions. Okay, if there is read operation in T1 and write operation in T1, there is no chance of conflict. If there is read option in read operation in T1 and write operation of on same data that is occurring on different transactions, say T2 or T3, then there will be an edge. Okay, so first let's consider Rx. Okay, this Rx is there, means T2 is executing. Now we have to search for Wx. Okay, conflicting pairs, from R to R there will be no conflict. So if we have R left hand side, we have to search for RW conflict now. Okay, just see, Rx is there, but from same data. Okay, if X is there in within bracket, we have to search for X in different transactions. Okay, so Rx is there, we have to search for Wx in different transactions after this time. Okay, so after this time, say it is time 1, we have Rx that is executing. Then what is remain? So first see the T1, is there Wx anywhere in T1? It is there. So from T2 there will be an edge to T1. One thing. Then after that, in T3 there is also WX, so there is also a conflict. There will be an edge from T2 to T3. Okay. Similarly, if we see T4, there is also WX, so we will have an edge from T2 to T4. Okay, very simple. If there is any conflicting pair for your executing operation at that time, then we have to create an edge. Okay, now uh, first time is gone, Rx is gone. Now coming to next one. Next is WX. Okay, for WX what we have to search for? We have to search for Rx. For WX we have all three opportunities of getting conflicting pairs. Okay, there may be WR, there may be RW, there may be sorry, there may be WR, there may be WW. Okay, so WX, from WX we have to search for WX or RX. Okay, in all three. So let's see. In T1 there is WX, but we have already provided an edge from T2 to T1, so there is no problem. We don't have to do again and again. If there is an edge, we have to consider it. Now for T3 there is WX. Okay, we have already an edge. For T4 there is also WX, so we have already the same edge. We don't have to create different means two times same edge. Okay, so WX is done. Now coming to the third one, there is WY. Okay, for WY we have to search for WY we have to search for RY or WY in different transactions. Okay, it is in T2, we have to search in T1, T3, T4. Okay, from WY we have to search for either WY or RY. Is there any? I am not able to see anything like WY or RY in different transactions, so there will be no edge from T2 due to this WY. Okay, now coming to the next time, it is done. Next is this T4. Now T4 is started executing. The first thing is WX. Okay, now we are done till here. We have to see from here, from this WX, and we have to search for conflicting pairs. Okay, very simple thing. Take this WX. Now search for T1. Is there WX? Yes. So there will be an edge from T4 to T1. Okay, it is done. Next, from WX to from T4 to T2, is there any kind of WX or RX there? Nothing is there in T2 after this time. Okay, it was there from previous timestamp, but now there is no any RX or WX after this time, so there will be no edge from T4 to T2. Now coming to T3, WX is there and WX is also there, so there will be an edge from T4 to T3. Okay, so it is done. Okay, now we have executed till WX. Now coming to WZ. Okay, next time is WZ. In WZ we have to, what we have to search for? We have to search for RZ or WZ in different transactions or other transactions. Okay, in T1 there is no Z, in T2 there is no Z afterwards, and if we see T3, WZ is there, WZ is there, so there will be an edge from T4 to T3. There will be an edge from T4 to T3, but there is already an edge, so we don't have to create another edge, so it is done. Next time sorry, now we come to T1, means WX. Okay, from WX the conflicting pairs will be WX RX or WX WX. So let's see. Afterwards, there is no RX or WX here. There is WX in this T3. Okay, so there will be an edge from T1 to T3. Okay, now there will be an edge from T1 to T3. Then there is nothing in T4. Sorry. So it is done. Coming to the next one, there is WX, but there is nothing in this these three transactions now. All are done. So these WX, WZ, they are free to be executed. These two operations, so we can cut them. Now the graph we have got is this. Okay, this is our precedence graph. Now we have to comment whether there is a loop, whether there is a cycle in this graph. If it is, then it will not be conflict serializable, but it may be view serializable. But if it has no loops, no cycles, then we can conclude that it is conflict serializable, means it is serializable. And if it is conflict serializable, with the concept we can say that it is also view serializable. Okay, so I think for checking the cycles or loop, we should go node by node. Okay, so if we have T1, okay, from T1 where we can go to T3. Okay, from T3 we cannot go anywhere. If we see, there is no outgoing edge from T3, so there will be no cycle with this node T1. Now coming to T2. If we see T2, there is no incoming edge, so there is no loop in T2. If we go from T2, we will go to this T4, then from T4 we will go to this T1, from T1 we will go to T3, but from T3 again there will be no outage, so there is no any there is no any kind of cycle there. If we go with this T2 to T1, then also we will end up in T3. There is no cycle. If we go from T2 to T3, again there is no cycle. So there is no cycle from these edges. Now we have last option left from T4. From T4, if we go, we will go to this T1, then from T1 to T3, and again there is a dead end. So we don't have any cycle, and there is no self loop like kind of this or this kind of cycle. There is nothing like these two thing, so we can easily say that it is conflict serializable. Okay, so if it is conflict serializable, it will also be view serializable. So the answer we have got is the C option. Answer C is correct. Got it? Again, I am repeating it because it is the basic question, and if you will be able to solve it, you will be very comfortable for any kind of questions related to it. Okay, so what I have done, I have created a precedence graph. So in precedence graph, what I have done, I have taken the operations, and based on timestamps, I have created the edges based upon the conflicting pairs among the transactions, sorry, among the transactions. And what are the conflicting pairs? Conflicting pairs are these three kind of operations occurring together. Okay, if there is write in execution, we get read in another operation. If there is read, there is write in another operation, transaction. If there is write and write, so this is consider this as a timeline. Okay, So first what will be executed, we will execute T2 because Rx is there. So if we see Rx, we have to search for Wx in different transactions. Okay, so we started with this T1, there was Wx, in T3 there was Wx, in T4 there is also Wx. So all Wx are there, so I created the edges from T2 to T1, T3 and T4. Okay, likewise I have created this graph, and in this graph if there is some edge repeating due to some conflicting pairs again and again, then we don't mark it. Okay, and in this graph what we have to search, we have to search for self loops or cycle. So like self loop is like this, cycle is like this. Okay, in between any two transactions, so there is nothing like this or this, so we can clearly say that it is conflict serializable. And if it is conflict serializable, it is also view serializable. You can see in the lectures and the theoretical in the book also. Okay, so it is done. Any confusion in this? Okay, so what was the question? So whenever there is a write, yes, if there is a write in different transaction. Okay, sorry. So if we have read in this, we have read in transaction I, say transaction I and J. So if we have read in transaction I, then on same data, okay, then we have to search for write. If it is there, then there will be conflicting pair. If it is write, if it is read, no problem. If it is write, then there will be problem. Okay, we have to search for read also and write also. Okay, so question 1 is done. It has taken a lot of time, but I tried to sum up. Okay, so it is the a better version. We have to just uh, select, means we have to uh, create the order of execution of all the transactions. Okay, so let's create the precedence graph quickly. So first we will execute Rx. So first there is T2, T1, T3 and T4. First we will search for serializability. Okay, you do by yourself, and what the answer you got, just the order of read and write doesn't matter here. uh, yeah, I think there is that depends, means on situations. Okay, so if it is we have to see if they are just one after one, then we have to just say 1 minute, what you are telling, order of read and write doesn't matter. No, order of read and write means I am just considering the timestamps. Okay, so what comes first should serve first. Okay, so if there is read first, I will consider read. The sequence they are coming, I mean, yeah, we have to search. We have to see for the sequence. Okay, the sequence they are coming, we will consider the transactions accordingly. Okay, so if there is read, so from read means it is occurring at T2. Okay, from T2 we have to search for there is Rx, so we have to search for Wx. Okay, so from for Wx in different transactions, not in T2. Okay, so if we search, T1 is free, in T2 there is Wx. Okay, sorry, T3. So there will be an edge from T2 to T3 and from T2 to T4 also. Okay, now it is done. If we see Wx, so Wx, there will be, we have to search for Rx also and Wx also. So Rx is not there and these two already have the edges, so if we consider it, not consider it, doesn't matter, the edges will be same. Next there is Ry. Okay, from Ry we have to search for Wy or oh sorry, only Wy. So for tree 3 we have to search for T1 there is ry, so from T3 there will be an edge, and in T4, T2 and T4 they will be free. So it is done. For wy we have to search for ry and wy. So same edge is there, there will be no another edge we have to create, and all these two are blank. Now coming to this one, T1, from T1 this ry is there, but it is coming just after this T3, so we have to search within this afterwards case. So there is no ry or y data operation there, so there will be no edge from T1, both are gone. Now there is rx. For rx we have to search, there is rx in T3. Okay, so there will be an edge from T4 to T3. Same for wx. Okay, so no new edge, same edge is there. Then rx is there, there is no x, there is wx, there is no x. Then there is wz. Wz is telling there should be an edge from T2 to T3. There is an already an edge, and wz is done. Okay, so this is the graph. Just see whether there is a any kind of cycle or loop is there. I don't think. If we start, there is no, so no loop. Okay, now what we have to do, we have to see for in degrees. Okay, okay, if there is an in degree, sorry, okay, sorry, so we have to search for in degree. First in degree should be 0. Okay, based upon that we have to create the sequence. How? Okay, we have in this graph we have to search for in degrees. Just see the in degrees, how many. Then so for T1 in degree is 1, T2 in degree is 0, for T4 in degree is 1. In degree means the edges coming to the node. Okay, here one node is coming, one node is going outside, so in degree is 1, out degree is 1. There is no incoming edge, so in degree is 0. There is 2 incoming edges, in degree is 2. Okay, now what we have to do, we have to search for in degree is equal to 0. So there is only one node or one transaction having this condition, so T2 will come first, means T2 will be executed first. Okay, now from T2 where we will go, we have to see it. T2 is done. After completion of T2, what we have to do, we will just erase it. Okay, the edges and T2 itself. Okay, now what is remained, we have to search for in degrees in these all transactions. Okay, so there is in degree 0, in degree 1, in degree 1. Okay, in degree 0 what the transaction is, that is T4. So this is T4. Sorry. From here only you can take B, but I will complete it for the sake of completion and your understanding, better understanding. Okay, so we have to just erase this T4 now. T4 is done. Coming to T3 and T1, in degree is 0, in degree is 1. Yeah, we have to start with in degree 0 and we will just erase one by one, and at last means we have erased the node with in degree 0 in next step. Now we have to recalculate the in degrees and again we have to write the sequence. Okay, so from T4 now in degrees lesser in T3, then from T3 what is remain, T1. Okay, so the answer here is, oh sorry, yeah, is my screen visible now? You just try it on chat. Yes, okay, thank you. Okay, not getting concept of in degrees. Just I'm telling, just telling. Okay. So the answer is B here. Okay. So means you want to say what are in degrees. So if we consider the graphs, okay, in graphs there are two things. There are nodes and there are edges. Okay. In directed graph, the edges will be directed. Means there will be from and to. Okay. I don't think it is reflecting. So it is reflecting very late. Yeah, it is the arrow starts from means there are two ends. Okay, if we write it like A to B, if we write from A to B, okay, consider there are two nodes in a graph A and B. Okay, in A and B, if we write from A to B, uh, is is there uh, from A to B I have written A to B is it is visible or not? Am I audible? I don't think it is visible. Yes, now I think it is visible. Yes, yes, yes. Okay. So the example I have taken is if there are two edges. Okay. Sorry, if there are two nodes. Say there are two nodes A and B. If I write from A to B, okay. So I will write it like this: A, then arrow, then B. Okay. Now here there is out degree, there is in degree. The out degree is from where from a node number of edges outgoing. Okay, so if I am telling there is an edge from this A to B, then the out degree of A will be 1. Okay, because there is one node, sorry, there is one edge that is going out from A, but the in degree for B will be 1 because there is one edge that is coming from any other node to B. Okay, if there are different means if there are many nodes, there is C, there is D. Oh, okay, I think again it's disconnected. Just a second. I am connected, but my pad is, yeah, now it is visible. My pad is actually disconnected. Just a second. There is some network issue. Let me connect with different network. So what are in degrees? In degrees means number of nodes. What the number of nodes? Sorry, the number of edges coming to any node. Okay. So if I am telling the in degree of B is 2.
Hello.
Yeah,
Have
yeah.
you shared anything?
Yeah, I am sharing. I am waiting for the network connection. Just hold on. I am just telling there is network issue due to heavy rain today. So just bear. Sorry for the interruption. Not able to connect again. Is it like single flow graph having incoming and yes, 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 same. Yes, same. I am telling the same. Yes, I am considering nodes as the transactions, not states. Transactions is the proper word for it. Uh, no, there is no bandwidth issue. There is actually issue with number of connections in the Wi-Fi. So I am connecting with different network. Yep, I think it's joined. Okay, okay, okay. Sorry, just a second, just a second. This- Mm, yeah, thanks. I think it's visible now. Yeah. Okay, I will try to be quick, little quick. Okay, thanks for waiting. So I think the concept is clear now. So if it is D, we have this edges from B. So the in degree will of B will be 3 here. Okay, in degree of C, D and A will be 0. Okay, it's quite similar. So we have to just create a graph and we have to just comment on the transactions which are having conflicting pairs. Okay, that's so simple. Okay. Sorry. So coming to the next one, what we have to do, we have to just create the conflict equivalent of the above schedule. This is the schedule. What we have to how to decide the first state? We have to decide the first state based upon the in degree having 0 value. Okay, so in the previous graph what we have seen, there was T2, there was T1, there was T4, there was T3. So from T2 uh, the graph was something like this. So T2 had this in degree 0. So first I selected this, then I wrote it here, then I erased this and the edges connected to it. Then I again took the T4, then T3. Same. I have done the same for all the cases. Okay. Now in this what we have to do for checking the conflict equivalent, we have to search for non-conflicting pairs. Okay. For non-conflicting pairs means there is no dependence in between. So if there is RR, we can exchange them. If there is any kind of Rx to WY, WX to RY means, or WX to WY, there may be Z or any other things. What I want to say is the data is different, then there will be no conflict in between them. Okay. So if there is no conflicting pairs in different operations, sorry, different transactions, we can just take them, we can just swap them. Okay. If we will get the similar means any kind of means if we can get any of these schedules given there, so one schedule is there, we have to search in these four. If we do such kind of operations and we get any of these schedules or any one schedule among these four, then we will say these two are conflict serializable, sorry, conflict equivalent. Okay, so let's get started. There is R2Y, W2Y. If we see there is W on Y. Okay, if there is W on Y, the non-conflicting pair will be R of X. Okay, R of X may be there, or anything on X, or any other than Y. We can consider it as the sorry, we can consider it as uh, consider for swapping. Okay, so if we see, there is Rx adjacent to it. Okay, so we can swap in between these two. What will be the next one? There is T1 and T2. If we swap in between these two, next 4 we can do it like Ry and Wy and so on. Okay, I'm just checking for these 4 first. Okay, so if there is Ry and Wy, okay, so if we swap in between Wy and Rx, because these two are non-conflicting here, these two are done in different data. So what will happen? There is Ry, there will be Rx, then there will be Wy, then there will be Wx. There will be no problem executing in this way. That will be equivalent because these the because these operations are mutually exclusive to each other. These are happening in different data. Okay, now uh, is there any kind of option which is having this kind of sequence? uh, I don't think so. There is either R and W on X is there, so we can do it once again. Okay, now we have this one. Again search for mutually exclusive or non-conflicting pair. Okay, so if we see, we have this option also. Okay, we can swap it like. Okay, so in next step what will happen? We can, okay, what is it? Again there is a problem, I think. Okay, just a second. uh, yeah, so not able to erase it, don't know why. Okay, I am writing it again. What will happen in next time step? T1 and T2 is there. I have swapped the Rx, sorry, Wx with Wy. Okay, next 4 are as it is. Okay, is there any option? No. Again we can swap. We can swap one by one. Rx with Rx and Wx with this Ry, because these three operations means these two operations are mutually exclusive, non-conflicting, and same for Wx also. It is happening on X and it is happening on Y. So we can, I am just skipping the step. I am just writing the next next one. So T1, T2, Rx, Wx, Ry, Wy, and next 4 onwards. So oh, what we are getting from here, T1, T2, then there is Rx. Oh, it's working now. Wow. Rx, Wx, then please join on time. Ry, Wy, then there is Ry, Wy, then there is Rx, Wx. So if we see clearly, it is option C, this one. You can check for other also. I have there is no time, there is very limited time, so I have to cover more things. The answer is C. Okay, C is the correct option. You can check for all these 3 options also by yourself. Okay, for just practicing purpose, whether you can give, and you can also check for whether these given schedules in between are these two conflict equivalent. Those you are mature enough. Okay, so coming to the next one, is it view serializable, possible number of view serializable schedules. So for possible number of view serializable schedules, what we have to see in case of view serializability are the 3 points. First is the initial read, then the second thing is final write, and third is the updates in between. Okay, so we have to stick with the initial read. Initial read should be the same, the final write should be the same, and in between the update should be the same, and then we can swap in between uh, the transactions. Okay, so in this there is no not any algorithm for it. We have to just see, we have to just means transform the transactions accordingly, and we have to conclude. Okay, so what we have to stick with, we have to stick with this, and this should not be changed. So what we can do, we can create an equivalent t1 t2 t3. So one view equivalent, we can say, if we take wx with it. Okay, and afterwards I proceed with all the operations. Okay, so if we see, this is actually the view equivalent of it. For checking purpose, you can take any value of x and apply any operation. Okay, so just consider rx, x is equal to 100, and just consider in between rx and wx, consider any operation. Okay, like x is equal to x plus 90. Okay, just do it like, and just print the value after execution of these operations. Okay, one view equivalent may be this. The second, what we can do, we can uh, bring these two as it is, we just step up this. Okay, so what we see, uh, there will be rx, there will be wx, there will be rx, then wx, then wx, then last wi. Okay, so these two are the possible ways, means taking the read and write operations together. In most of the example, you will see where we have to create this kind of view serializable schedule, we just took the operations combinedly. Okay, so there are two options, there are two possible number of schedules. If we see t3, there is only one operation, we can't do anything with it. If we see wi, we should not touch it, and there is no ry anywhere. So if we have just two options, we can take these two together or these two together. Okay, so what will happen if we will take these two together, we are indirectly telling that just execute t2 first, then go to anywhere, either t2 or t3 or t1. Okay, otherwise what we are telling ki, we should, if there is t2, first complete the t1, then again come to execution to t3, then again. Okay, so what we have to means clarify with in case of view serializability, that if there is an edge, if there is an edge from t1 to t2 and then t2 to t1, we have to ensure that first any one of these two should complete, then the other one should execute. Okay, we have to either miss this edge either, or we have to cancel this edge. Okay, if t2 has ry, then we club them together. Yes, why not? No, 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 no. T2 has RY, then we cannot club. We can club within the same transaction, just to ensure that one transaction is occurring at a time, then we are allocating the machine to any other transaction. Okay. Oh, so coming to the next one, this is very simple one. Just it is based upon the concept of wound weight deadlock prevention. So there are three transactions, T1, T2, T3. T2 is having this holding the data items, okay, and there are timestamps given. It has 12, it has 16, it has 20. So T2 is having data item this time. We have to comment on the situation, what will happen. Okay. So in wound weight deadlock prevention, what happens? The older one, older one means having less timestamp, actually rolls back forcefully. Okay. So which is the older one? There is a less timestamp. The T1 has less timestamp. So T1 will roll back. Okay. Will force rollback to T2, and the next one means younger one means having more timestamp, that actually waits. Okay. The older one rolls back forcefully, and the younger one actually waits for the T2 to release the acquiring transaction to release it. Okay. So just mark the options. In one it is telling T1 will wait for T2 to release. That will be incorrect because T1 is the older one. T3 will wait for T2 to release the item. Yes, that is the correct one. Okay, because T3 is the younger one. Then transaction T1 will wound force rollback of T2 to release the data item. Yes, that will be correct because T1 is the older one, and T3 wounds, that is also incorrect because T3 is the younger one. So answers are B and C together. Okay. Coming to the next one. Yeah. Can we apply the process that we followed, finding the number of serials, finding number of conflict? Yeah, you can try, but why we will apply it here? We have to just comment on the deadlock. Okay, that is simple concept. If you go through the lecture PPT, there is a simple thing. There is a heading of it. Just read it, you will get it. So next is uh, we have to comment on the deadlocks. It will be there in S1 or S2 or not. Okay, so sorry. Mm, let's see. In this S1 schedule, if we check, it first takes the exclusive lock on A, then reads A, then exclusive lock on B, then unlocks A, then unlocks B. Then T2 takes exclusive lock on A, then unlocks A. So there is no any condition where deadlock can occur. It is easily executing. Okay. So S1 will not suffer from deadlock. That is the one thing. No deadlock here. Now comment on S2. Will there be deadlock or not? Just comment on comment section. Okay. I am telling. So there is a shared lock. Then shared lock is having this A. So if shared lock is having A, anyone can check for A with shared lock again. But if it is in exclusive lock XA, then there is no option. Okay. So it's share locked on B, and there is say there is exclusive lock on this A. That is not possible. Okay, and again if we come afterward, there is exclusive lock on B also. So from here we can conclude easily that S2 will suffer deadlock. Okay, so answer is S1. No, S1 is not. S1 will suffer from deadlock. No, S1 will not suffer deadlock. S2 will suffer from deadlock. Yes, C is the option, and D neither. No. Okay, so again, if there is a matrix given in the PPT, you just go through it. There is given, if there is shared lock you can apply on different transactions. There will be no problem. But if there is a shared lock and there is an exclusive lock, then there will be problem. Okay. Again, coming to the next one, there is rigorous and strict. We have to comment on rigorous and the strict two-phase locking protocol. So in rigorous, what happens? Just I am writing it in strict um, two-phase lock. What happens? We have to all exclusive lock, say on A, held by the transactions be released until after the transaction commits. Okay, and in case of this rigorous two-phase lock, all thing will be same. There will be all shared lock and exclusive lock. It happens for all these two. Okay, so just see these conditions and comment on it. This is very simple now. So both T1 and T2 follow the rigorous two-phase locking. So if we see uh, in case of T1, we can see that there is commit before unlocking. Okay, so all XA, all means exclusive locks uh, are released until after the transaction commits. So after the transaction commits, the exclusive lock XB is released. So regress one is satisfying, but for T2 commit is after it. So there is nothing like regress or any kind of this S2PL. So first is no, second is no. There is C and D. Regress T2 follows strict two phase. No, commit is after unlocking. Then it is correct. You can see T1 follows rigorous two phase locking. T2 does not follow strict two phase locking. Okay, just read the concept. You can comment on it. So time is done for today. Just finish this question and we will be done. Uh, sorry. Uh, there is we have to comment on these two schedules. If these are recoverable or not, and if these are cascadeless or not. So if we comment on cascadeless, what we understand is if one of the transaction is executed, then it means commits its values, then after the another transaction starts taking values. Okay, so if we see S1, we can easily comment then that after writing the value of t1, it is committing, means it is now permanently storing the value to the database, and then this value is retrieved by t2. So that is the proper way to tell that it is actually cascadeless. Okay, so s1 is cascadeless for sure, but in case of s2, is it cascadeless? No, because it is not committing, it is writing, then the written value is just it is not written in database, but it is now going to t2. So if we will fail anywhere, we have to means we have to clear these values also. But if in this case, if we will fail, we have to just revert these value only. Okay, so it is actually cascaded, it is cascadeless. Okay, now we have to comment on recoverability. So the transactions will be recoverable if all the operations are done before the commit. So if we see in both cases, these are committing the values, means commit is there just after all the operations, so both are actually recoverable. Now comment on these two. So s1 is recoverable, s2 is cascadeless. That is totally wrong. S1 is cascadeless, S2 is recoverable, yes. Both are cascadeless, wrong. S1 and S2 are recoverable, yes. So answers are B and D here. Okay, getting it? So that's all from my side. Thanks for bearing some network issues. I am not well today. So next week is the, I think, last week for the problem solving session. So I will request all of you to join, and also if there are anything you want me to cover, any kind of example from my side, or any kind of concept, those are unclear in the lectures, you want me to cover with the help of any problems, real world problems, just comment on the discussion forum for that. Okay, so thank you all. If there is any problem, just write on discussion forum, I will try to address them in next week. Okay, so ending this meeting, thank you.